Hey guys, it's me, Mr. Tardy, here to record and present your reading for 20-3, Chapter 20, Electricity, Section 3, Electric Circuits, from our book, Glencoe's Introduction to Physical Science, 2005. All right? So, here is the reading. Please pay attention. Feel free to take notes, though you probably will be fine. Afterwards, you'll be passed out the paper. Try to complete the paper to the best of your capabilities. It will be due on Tuesday when I am back, okay? So, or whenever. Controlling the current. When you connect a conductor, such as a wire or a light bulb, between the positive and negative terminals of a battery, electrons flow in the circuit. The amount of current is determined by the voltage supplied by the battery and the resistance of the conductor. To understand this relationship, imagine a bucket with a hose at the bottom. If the bucket is raised, the water will flow out of the hose faster than before. Increasing the height will increase the current. So you take a look at this person, water's flowing out, but if you raise it up, there's more gravitational potential energy, which means that the hose can flow at a better rate. You also take a look, it's not curved, so there's less complications for the hose to go. Recalling what we were talking about yesterday, there's such thing as a current and a circuit. So you may be remembering a battery. A battery is a tool that stores electricity via chemical energy. Okay? And if you want to make a circuit, you have to take that electricity and connect a wire. Maybe you have some pieces like a light bulb to which the wire's connected. And then there will be the coil inside here, and it lights up. Bing, ding, 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 ding. And then the wire goes back. So we can see that a full loop is made. And the loop is known as a circuit. For a circuit to be good, it has to be closed. Very important thing to remember. Think back to the pump and the water wheel in figure 10. Recall that the raised water has energy that is lost when the water falls. Increasing the height from which the water falls increases the energy of the water. Increasing the height of the water is similar to increasing the voltage of the battery. Just as a water current increases when the height of the water increases, the electric current in a circuit will increase as the voltage increases. If the diameter of the tube in figure 15 is decreased, the resistance is greater and the flow of water decreases. At the same way, the resistance of an electric circuit increases, the circuit decreases. What is this saying? Well, in wire, there's this thing called resistance. And more resistance means less electrical flow. All right? You have more resistance, you have less electrical flow, which causes like more pressure to come out at the same time. That's here or there. So how do you get more resistance? You make your wire long and you make your wire thin. And then sometimes there's certain materials that are going to be better than others. But we'll talk about that later when it comes up. Oh, one more thing. You want to increase the voltage. You say this is like a 1.5 volt AA battery. Now, certain toys or remotes or whatever you use that uses batteries might need multiple batteries. And you put them somewhat like this. You have the positive, the negative, the positive, the negative. Or maybe if you're talking about a remote, in the back, you have your battery slot right here. With this being the positive, this being the negative, and this being the positive, and this being the negative, right? What's happening? Well, when you put it up and down like that, you allow the electricity to go through the batteries and a circuit can be completed. You put the positive right here like this, the circuit can go to the upper end of the battery, come down to the negative of the second battery, and then flow back through. You're allowing electrons to flow in a, I don't want to say positive. You're allowing electrons to flow in a natural state that supports electrical flow. And because that's the case, you guys are getting, well, good electricity. Now, if this is 1.5 and this is 1.5, the total voltage combined is obviously going to be 3 volts. If this is a 9-volt battery and this is a 9-volt battery, then the combined voltage will be 18 volts. Does that make sense? Topo Chico. So, Germans. When it comes to science, there's very few people that do it better than the Germans. Albert Einstein was a German. And so is this person, George Simon Ohm. George Simon Ohm carried out experiments that measured how changing a volt in a circuit affected the current. He found a simple relationship amongst voltage, current, and resistance in the equation we call Ohm's law. We write this as volts, which we use the symbol V, is equal to current, which we use the symbol I. Why we do that, I do not know. Then multiplied by resistance. And we use the symbol R. Now, resistance is also measured in ohms. And so you may also see the symbol omega, right? So ohms and omegas measures resistance. Okay? Now, you may be concerned, like Mr. Tardy. In an equation, I don't have I and R. I have V and I. You just need to remember simple translations. You have I times an R. How do you get R by itself? Divide by I. V over I, or voltage divided by current, is equal to resistance. Same thing. Current is equal to voltage divided by resistance. This is multiplication. These are like numbers. No, they're not the same X, Y you're used to, but that's the point in the algebra I'm trying to teach you, is that it is the same thing overall. I don't want crap. My eraser. I don't know. Anyways, according to Ohm's law, when the voltage in a circuit increases, the current increases, just as the water flows faster from a bucket that's raised higher. However, if the voltage in a circuit does not change, then the current in the circuit decreases when the resistance is increased. All right, so here we have a little practice problem. A light bulb is plugged into a wall outlet. Gather your little night light. If the light bulb has a resistance of 220 square, I think that's supposed to be your omega. So we have 220 ohms. Talking about resistance, so that's how I know. The current is 0.5 amps. 0.5 amps. What has to be the voltage provided by the outlet? So volts equal what? Now, if you just remember, we got V equals IR. Or if you want to rewrite that, V equals A omega. And so we have V is equal to 220 times 0.5. 0.5, another way saying that's half. So what's half of 220? Darn tootly rootily, it is 110. But we have a word problem, so we should have a word answer. 110 volts. Now you put the V, you're fine. I'm going to put volts just because I can. All right. So, yeah, that's what they got. And they say that if you did 110 volts divided by 220 omegas or ohms, you should get 0.5, which is true. There's a couple of more practice problems right here. If you want to try them out, feel free. We are going to be dealing with these calculations a bit, so it wouldn't hurt to have them go around. Maybe we'll come back towards them at the end. But here is the meat and potatoes. Get that broccoli out of here. We're done with it. We want series and parallel circuits. This is the tasty stuff. Woo! Circuits control the movement of electric current by providing paths for the electrons to follow. For the current to flow, the circuit must be unbroken. That's what I was saying earlier. Have you ever been putting up holiday lights and a string that would not light because a single bulb was missing or had burnt out? You can't figure out which one it was? Maybe you've noticed that some of the lights don't go out no matter how many bulbs burn out or remove. These are two different types of circuits. There is the series circuit. I'm going to change this to, like, I don't know, let's do purple. There's the series circuit, and there is the parallel circuit. In a series circuit, the circuit has only one path for the electric current to follow. If this path is broken, then the current will no longer flow and all the devices in the circuit will stop working. If the entire string of lights went out when one bulb is removed, then the lights in the string are wired as a series circuit. When the bulb burnt out, the filament of the bulb broke and the current path for the entire string was broken. In a series circuit, electrical devices are connected along the same current path. As a result, the current is the same through every device. However, each new device that is added to the circuit decreases the current throughout the circuit. This is because each device has some form of electrical resistance. And in a series circuit, the total resistance to the flow of electrons increases as each additional device is added. By Ohm's law, if the voltage does not change, the current decreases as the resistance increases. So what's this saying? You don't change the battery, you don't make it more powerful. The more stuff you add, the less good the flow is going to be. So you can't keep putting more and more and more on there. All right. So you want to minimize it. So a series circuit is one big loop. You got, oh, that's pink. I want purple. Come on, purple. Woo. You got your battery. We dig it. And you have one path. And that's what makes it a series circuit. There's only one path. You take your scissors, you snip it, you're gonna get electrocuted a bit. But after you get electrocuted a bit, the circuit's not working anymore because there's no way for the electricity to flow. Honestly, series circuits, kind of a mid-tier circuit. We like to do parallel because it does everything series can but better. But when you're introduced to circuits, it's so much simpler to do a series circuit. All right. Now you take a series of series circuits, and now you have a parallel circuit. What would you do if you wanted to watch TV? And in order to do that, you had to turn on the lights, the hair dryer, the fridge, I mean, some of that stuff's on. A good example. You gotta turn on like your lights, you gotta plug in your laptop, you got to, I don't know. Sorry, anyways. And every other electrical appliance in the house to do so. That's what it'd be like if all the electrical appliances in your house were connected in a series circuit. But schools, houses, and other buildings are wired using parallel circuits. Parallel circuits is a circuit that has more than one path for the electric current to follow. I showed in figure 17 right here. The current branches so that the electron flow through each path. If one of the paths is broken, then the electrons continue to flow in the other paths. Adding or removing additional devices in one branch does not break the current path, so the devices on those branches continue to work normally. In a parallel circuit, the resistance in each branch can be different depending on the devices in said branch. The lower the resistance, the more current. So current in each branch can be different. So this gets a lot more complicated, but it allows for easier processing. So we have the battery. We connect it to a light bulb. But then we also, at this light bulb, connect it to a second light bulb. Right? And theoretically, what happens is that if we break this light bulb, you take a big old hammer and smash it, well, the electricity can loop through the first loop, so the circuit's complete. You take a big old hammer and smash the middle light bulb, well, the electricity can loop here because the wire's connected there and be complete. Now, right now, the electricity is looping through both things at once. So, technically, there's a lot more power being used, a lot more volts, and there's a lot more light being produced. Say you want to get individual lights on or off, that's when you get into switches, and that's something we can talk about later. Just know, series is one, parallel allows multiple, okay? Now, you may have been outside or you may have been in your basement or something and you see a big metal box on the wall. That may have been the fuse box. Electricity generates heat, as we know. Electricity uses a lot of power. So it's important to protect our houses from overloading on electricity so they don't get burnt down. In a parallel circuit, the current that flows out of the battery or an electric outlet increases as more devices are added to the circuit. As the current through the circuit increases, the wires will heat up. To keep the wire from becoming hot enough to cause a fire, circuits in the house and other buildings have a fuse or circuit breaker, like those shown in figure 18 here, that limit the amount of current in the wiring. When the current becomes larger than 15 amps or 20 amps, a piece of metal in the fuse melts or the switch in the circuit breaker opens, stopping the current. This cause of overload can then be removed and the circuit can be used again by replacing the fuse or by resetting the circuit breaker. So fuses are a bit more of old technology. Fuses are what were used to complete the circuit. However, if it gets too hot, because that's how the fuses were designed, it melts and you are not getting your house burnt down because since it melts, the electricity stops flowing, right? It's broken. There's no closed connection for the electricity to keep going. So you break your fuses in order to save your house. Now, this is a bit more of older technology. Modern day, you're probably going to have circuit breakers. Circuit breakers are switches. It's like a little light switch. You just flip it off, flip it on. Nice things about each circuit breakers, you really don't have to replace too often. Yes, they get old, worn down, and will need to be replaced, but not as like a fuse. However, with the fuse, you kind of know which one broke. It's an easy tell. Okay? A lot of times, overload can be caused by using a lot of electricity at once. So, the microwave can use a lot of electricity, right? Here's your microwave. Generating that amount of heat, it takes a good amount of energy. Then you got your toaster that can generate a lot of electricity. And then you might also want to have your tea in the morning. And your tea needs hot water generated by a kettle, an electric kettle by chance, right? So you're plugging these all into the same power source, the same wall outlet. You know what? My wall outlet only has two, so I'm gonna plug in a multi-port extender. So boom, 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 boom. Wow. Okay. And I plug in my kettle, and I plug in my toaster, I plug in my microwave, and I overslept a bit, so I'm gonna heat up my toast. I'm gonna microwave my milk, and I'm gonna make my tea for later. I don't know. And uh-oh, the power went out. The only in the kitchen, only in this area of the kitchen. That's because you used too much energy. You've overloaded your fuse. So instead of burning your house down, you'd have to go and reset it. All right. Electrical power. When you use an appliance such as a toaster or a hair dryer, the electrical power is converted into other forms of energy. The rate at which electrical energy is converted into other forms is called electrical power. In an electric appliance or any electric circuit, the electrical power that is used can be calculated from the electrical power equation. Power, watts, is equal to current, amps, times volts, in, well, volts. So, ooh, that's a W. W equals AV. Watts equals amps times volts. The electrical current power is equal to the voltage provided in the appliance times the current that flows into the appliance. The electrical power equation, the SI unit of power, is the watt. Power is measured in watts. Table 1 lists the electrical power used by some appliances. So an old computer will use like 350 watts. More modern computers will use around 400 to 500. Color TVs is 200. As our TVs get more and more technologically advanced, they tend to use less watts. The hair dryer uses 1,000. Microwave uses 700 to 1,500. So here's a little practice problem. Your volt is equal to 110. Your current's equal to 0.55. Well, we know we want to calculate our power. So our power is current, I, times volts, V. So 0.55 times 110, that's 60 watts. All right. We should be finishing up stuff soon. Yeah, a couple more pages. We'll run this up quickly, let you guys get to work. Okay. Power is the rate at which energy is used, or the amount of energy that is used per second. When you use your hairdryer, the amount of electrical energy that is used depends on the power of your hairdryer and the amount of time you used it. If you used it for 5 minutes yesterday and 10 minutes today, you used twice as much energy as you did yesterday. Using electrical energy costs money. Again, stuff ain't free. Okay? You want to use something, you want to buy something, you want to eat something, it's going to cost money. Because even if you think something should be free for use, there's still labor costs that need to be provided for. Water is a human right, but clean water is not. Someone's got to go get that water, they got to purify it, and then they got to ship it. That purification and that shipping is human labor, and that needs to be paid for. All right. Using electrical energy costs money. Electrical companies generate electrical energy and sell it in a unit of kilowatts per hour, so 1,000 watts every hour. They sell it to homes, they sell it to schools, they sell it to businesses, any place that uses electrical energy. 1 kilowatt hour is the amount of electrical energy that 1 kilowatt of power would be used in a continuous hour. This would be the amount of energy needed for light 10 100-watt light bulbs for an hour, or 100 light bulbs for 10 hours. An electric company usually charges its customers for the number of kilowatt hours they use every month. The number of kilowatt hours used in a building, such as a house or a school, is measured by an electric meter, which is usually found attached to outside to the building. Have you ever had a mild shock? You probably felt that the only mild tingling sensation, but electricity has a much more dangerous effect. In 1991, electric shocks killed an estimated of 490 people in the United States. Here are some safety tips to help prevent electrical accidents. Electricity is extremely dangerous, okay? It's really cool. It's the dangerous toys that attract us the most, but we need to be careful and safe. All right? Never use appliances with frayed or damaged cords. So you might see your toaster, and your toaster has a wiring issue where it's kind of ate up in the center, right? And so if it's frayed up in the center, don't use it. The minimum you're going to want to do is get some electrical tape, tape designed for electrical appliances, and you're going to want to wrap it around. Okay? That exposed electrical cords can shock and kill you. Unplug appliances before working on them, such as when prying toast out of a jammed toaster. Okay? You need to make sure that you're not receiving electricity. Work on your appliances, but there needs to be no electricity in the device. All right? Does that make sense? So unplug it. Avoid all water when using plugged-in appliances. Water conducts electricity really well. So don't be wet. All right? Don't wash your hands before working on electricity. In fact, try and keep them dry. Dry skin does not conduct electricity. It's a great insulator. Never touch power lines with anything. Power lines contain an insane amount of electricity. One touch will kill you. You can find videos online of birds accidentally touching the power lines. They'll peck it or something. They'll fly into it by accident, clip it with their wing, and they're instantly dead like that. It's deadly. Always respect warning signs and labels. These signs are for a reason. Okay? There is a label for a reason. The company doesn't want to get sued. If you hurt yourself on their appliance and you were not warned, you can sue them. So what are they going to do? They're going to put labels to say, we warned you. You dealt with the consequences. You're not suing us, right? If a company puts the label on, trust it. They don't want to get sued. Electric shock. You experience an electric shock when an electric current enters your body. In some ways, your body is like a piece of insulated wire. The fluids inside your body are really good conductors. The electrical resistance of dry skin is much higher, so be dry, not wet. Skin insulates the body like a plastic insulation around a copper wire. Your skin will help keep electric current from entering your body. A current can enter your body when you accidentally become part of a circuit. When you receive a deadly shock, depending on the amount of current that flows through your body. The current that flows through the wires connected to a 60-watt light bulb is about half an amp. This amount of current entering your body could be deadly. Half an amp is deadly. 0.001 amps can be painful. On average, more people are killed every year by lightning in the United States than by hurricanes or tornadoes. Most lightning deaths and injuries occur outdoors. If you are outside and you see lightning or you hear thunder, you take shelter indoors immediately. If you can't go indoors, you should take these precautions. Avoid high places to get low and open fields. Stay away from tall objects such as trees, flagpoles, or light towers. Those are more up, so they're more likely to pull the electricity into them. Avoid objects that conduct current. Avoid water. Avoid metal fences. Avoid picnic shelters and metal bleachers. All right? Arguably, one of the best places you could go if you're in a lightning storm, see if you can get to a dugout. Dugouts tend to be made out of wood. They tend to be low to the ground. Best position. You see here a threshold, 0.005 amps is a tingle. 0.01 amps is where you start to feel pain. 0.1 or 0.01, you can't let go. So you're holding on because you are seizing up, your nerves are not allowing your muscles to ungrip. At 0.5 to 0.1 amps, you're going to start having difficulty breathing. Your lungs are going to start, failing. And at 1 amp, so half an amp to 1 amp, you are starting to experience heart failure, which will lead to death. Electricity is something to not be feared, but to be respected. Okay? Electricity is everywhere in the modern age. We can't avoid it, but we have to respect it. All right. So I'm going to ask that you work on your paper. Should be passed out. Get the full paper done. Please have it ready for me on Tuesday. Appreciate it. I will catch you on the flip sizzle. Bye-bye.